This is going to be the first of two videos to explain how we answer a question such as the one shown on the paper here, where we've got some ammonium chloride being dissolved in water and the temperature of this decreases, so it must be an endothermic reaction. So we call this calorimetry, where we use a temperature change to work out the amount of energy being absorbed or released, and then we work out the enthalpy change from that because we know how much of each substance was involved in the chemical reaction. So, in case your screen's a bit small, I'll just read this out. It says when 10.6 grams of ammonium chloride, NH4Cl, is dissolved in 65.0 ml of water, the temperature of the water changes from 20.9 degrees Celsius to 11.5 degrees Celsius. So that's a decrease in temperature, so I know this is an endothermic reaction. One of the little tricks I remember is endo has 4 letters, cold has 4 letters. This is getting colder. It's getting cold. It tells us the mass of the final solution is 75.6 grams. That's a really big hint for what our mass is that we're going to work with in this calculation. It also tells us to assume the heat capacity has not changed, even though it's got something in it, because that's the heat capacity of water, 4.18 joules per gram per degree Celsius. It gives us the molar mass of ammonium chloride, so I know that. I need that at some stage. And it's asking us to report an enthalpy change, which is in kilojoules per mole. So I know I'm going to need some equations that link energy, Q, with mass, specific heat capacity, and a temperature change. And I know that I'm going to need to work out the number of moles of something in this as well. And I've got a molar mass, so I'm probably going to link N, M, and MR with this. So in our first video, what we're going to look at, you notice I've got a calculator because it's a useful thing to have for these. My first step is just going to be calculating the amount of energy, in this case absorbed, so because it's getting colder, so that heat energy is being absorbed out of the water molecules by this dissolving reaction. So in order to break the ionic bonds between the ammonium ions and the chloride ions and turn it into a solution. So to do that, we've got to remember this equation. Now you might have remembered it as Q equals MS delta T. S and C are interchangeable. I'm using C because that's the specific heat capacity of water, and this was an aqueous system. So temperature change is the delta T. I think that is quite obvious there as to how to work that out. The bigger number minus the smaller number equals that. If it's exothermic, still do the bigger number minus the smaller number, because we can adjust for that being negative later. We can actually adjust for that being exothermic in step 3, which will be a later video. After you've got your temperature change, you're often given the specific heat capacity in the question. Do note that it's in joules per gram per degree Celsius, so we're probably going to need to change this into kilojoules at the very end. We might as well work with this to start with, but at the very end, when we have our Q, our energy value, we're going to convert that into kilojoules because it's more useful. Our mass, now this is the hard bit. This is the mass of the substance that is actually changing temperature. And it's the water that's changing temperature. But as soon as you put something else into it, you change the mass that we've got. So we've got 65 mils, which is 65 grams, because water has a density of 1 gram per mil. So 65 grams, but we've put this 10.6 grams of ammonium chloride into it. So actually the total mass of what changes temperature is this 75.6. They've been really nice in this question and given it to you. They don't always. So if you have something being dissolved into something, you have to add the mass of the solvent and the mass of the solute together. So I've done that. I've done my 65 mils, which becomes 65 grams, plus my 10.6, and sure enough, it's the 75.6 that they gave us. Then I just multiply those out, and I get 2970.4752 joules. I'm then going to round it off to 3 significant figures, because in these questions, it is usually 3SF. Now, technically, it should be 2 because of this 9.4 degrees Celsius change, but the actual original values were to three significant figures, 20.9 and 11.5. So I'm going to persist with that. So three significant figures for my final answer, and then I'm going to turn the joules into kilojoules. So I'm going to divide this number by 1,000 to get it into kilojoules, maintaining my three significant figures. In the next video, you're going to see how we take this number and turn it into an enthalpy change for this reaction.